Hey everyone, this is Mr. Mott. What I want to do is go through the periodic table, look at some periodic trends and how we can derive them from atomic size or atomic radius. So first, what I want to do is go through a little bit about the structure of the periodic table and how it came to be, and look at some of the scientists that were trying to solve this puzzle. So first, one I want to make mention of is Johann Dobereiner. He saw some patterns within groups of three, and so he saw that certain groups of three had similar properties. John Newland saw groups of eight. Lothar Meyer decided that he was going to arrange the periodic table in terms of increasing atomic mass. But Dmitry Mendeleev sort of perfected that, and the reason that he's considered the father of the periodic table is because he was able to predict the properties of elements that had not yet been discovered. When they were discovered, his predictions were really accurate according to the actual data that was collected. So he is known as the father of the periodic table. On our periodic table, we call the rows periods. And so what we say is on our periodic table that there's periodicity as you go from left to right within that row or within that period. Groups are sometimes called families or vertical. The group in the red there are the alkali metals. Actually shouldn't include the top box there, which is hydrogen, which is not an alkali metal, but it is in that first column there. Alkali metals are very reactive with water. The next group in orange there are your alkaline earth metals. They're reactive with water, but to a lesser degree. The group in white are your transition metals. A lot of our common elements are in there, like iron, nickel, zinc, copper. On the far right, we have our noble gases. These are very non-reactive gases, and for a while they weren't known because the way the periodic table was arranged was by reactivity. And so since they were not reactive, they weren't initially in there. Next to the noble gases, we have our halogens, and the halogens are very reactive elements. And we're going to look at more of a reactivity a little bit later. As far as how our periodic table is arranged with atomic size, most students would guess that as you go down a group, the atomic size gets bigger. And as you go from left to right, the atomic size will get bigger as well because you've got more protons, you've got more neutrons, and everything like that. However, once we look at the data, we see that one of the trends that they thought was true going up and down, going down a group, the atomic size gets bigger, but from left to right, it does actually get smaller. So if we look at within a group, the reason that the atomic size gets bigger is that you have increased number of energy levels. Sometimes these are called shells where the electrons live. And even though this isn't the most accurate model that we have today, it's a pretty useful and pretty concrete example. And so as you go down a group, you'll see that from hydrogen to lithium, sodium to potassium, that you get one additional ring, and that increases the atomic size. Within a period, though, we notice that the atomic size gets smaller. And so the reason is, kind of going back to that shell diagram, is that as you go from left to right, while you are increasing your number of protons and neutrons and electrons, all those new electrons are within that same shell. And so as you go from left to right, you're increasing your protons and your electrons, which increases the attractive force between them, and that's what causes the decrease in the atomic size. So from this atomic size, we can try to derive some trends and how we can sort of understand the trends based on atomic size. So ionization energy is one trend that we would want to know, which means the energy needed to remove an electron. So as we go down a group, you've got a bigger atomic radius, and this is actually as you go down and also to the left. You're going to have a bigger atomic radius, which means the electrons are farther away from the nucleus, which means it takes less energy to remove an electron. So it has a low ionization energy. And this leads to some trends that are very important. So in terms of reactivity, as you go down and to the left, those are your metals. And so as you go down to the left, you're going to have a high metal reactivity. You're going to have a low electronegativity because the electronegativity is how well that atom holds onto its electrons. and because these atoms have a tendency to lose electrons, they become positively charged as ions. Here's our picture again of our atomic size, and right now we're going to look at it within a period. So if we're going left to right, we want to think about our ionization energy. How easy is it going to be able to remove an electron? Well, as you go from left to right, the atomic radius decreases. So that means that the electrons are closer to the nucleus, which means that it would take a lot of energy to remove that electron. And if it takes a lot of energy to remove an electron, then the tendency is actually it won't want to lose an electron. It actually wants to gain electrons. So as you go up and to the right on our periodic table, you end up having a high nonmetal reactivity because those nonmetals want to pull on electrons. They have a greater attraction for the electrons. That's because, sort of linked with their high electronegativity, they want to be able to pull on the electrons away. They want to take electrons, which means they're very reactive as that electronegativity increases. And since they want to pull on the electrons and take electrons away from other elements, that means that they're going to be negatively charged as ions. So here's our trend again in terms of atomic size. It's going to be one that you want to remember. And on your papers now, on your blank periodic table, we can start drawing in some of those trends. Okay. First, we should know where our metals, nonmetals, and metalloids are on our periodic table. There's kind of a staircase which separates your metals and your nonmetals. Your metalloids are along the staircase, and we can talk more about that later. But right now, we're going to talk about trends and kind of summarize what we just did. As you go down and to the left, your atomic size increases. It's a really important trend to know. Because the atomic size gets bigger, that means that the electronegativity is going to decrease. It's going to be easier for that atom to lose an electron. And if it's very easy for that atom to lose an electron, it doesn't take very much energy to pull that electron away. That means that these metals in the bottom left are going to be very, very reactive. Okay. As you go up and to the right, the atomic size decreases. So that means that the electronegativity is going to increase, meaning that as you go up and to the right, those elements are more likely to want to pull on the electrons that are involved in a type of bond, which means that as you go up and to the right, those nonmetals become more reactive. And it also makes it that those nonmetals don't want to give up their electrons. They want to hold on to it. So it'd be very, very difficult to be able to pull an electron away from, say, fluorine, which is your most electronegative element. All right, so hopefully this has given you some insight into some periodic trends. My feeling is that if you remember the trends in atomic size and you know the definition of electronegativity and ionization energy, and you understand that metal reactivity has to do with losing electrons, non-metal reactivity has to do with gaining electrons, then I think you're going to be in good shape. Thanks for watching.